Hello, everyone. Let's take a look at section 4.5. This is a continuation of chapter on vector spaces. So in section 4.4, actually, the previous lecture, we talked about spanning sets and linear independence. Now we're going to put those to use in section 4.5. So section 4.5, we're going to talk about basis and dimension. So first of all, a basis, the bases, the plural form of basis, bases form the building blocks of the entire vector space. Okay, so that's what the vector space is made up. It's made up of a whole bunch of bases vectors, and later we'll note that, well, what is a basis? What a basis does geometrically is that it really imposes a coordinate system of the vector space. So it gives you kind of a new view of the vector space. Now, I'll clarify that statement later on, what I mean by a coordinate system. Okay, so first, what is the definition of a basis? Very simple. So suppose we have again a set. Okay, we have a set of vectors in the vector space. This is called a basis when following conditions are true. So in order for that set to form a basis for the vector space, these two things must hold. Okay, now one, the set must span V. Now remember from previous section, we said a set S, which is a subset of vector space V, spans V if every vector in V could be written as a linear combination of vectors in S. In this case, V1, V2, so on and so forth, all the way up to Vn. So that's the spanning part. If you need a review on the spanning sets and what does the span mean, please watch the previous lecture on section 4.4. Okay. Number two, to be a basis, so first it has to span the vector space. Number two, the set S has to be linearly independent itself. Okay, so the linear independence, two things are going on in here, by the way. So the first part, the set spans V, this guarantees that there are enough bases or basis vectors to provide coordinates for all vectors in vector space V. Okay, if you think of a basis again as describing a coordinate system, just like your XYZ coordinate system. Okay, so that's what bases do. It guarantees that there's enough vectors to provide the coordinates XYZ for all vectors. And what the condition 2 of linear independent guarantees is that it guarantees there is no interrelationship between the basis vectors themselves, right? Remember, S is a set of vectors. So if they're linearly independent, means you cannot write them in terms of one another. Okay. So that's what basically a basis is. Simple definition. Now, of course, if V has here basis of containing a finite number of vectors, then we have a finite dimensional vector space. Otherwise, you have infinite dimensional vector space. Okay, an example of those are cited here. So let's take a look at, for instance, this example that's already in the book. So we have a set of vectors. The question, does this set of vectors represent a basis? Now, if you graph these points, if you plot these points on the XY coordinate system, these actually provide the coordinates of a point, the bases do, right? So to show that this set is actually a basis, we need to show that it spans the vector space and it's linearly independent. Now, the author says, well, earlier in previous section, we showed that it spans R3. And I'll tell you how to do that. The easiest way to show that a set spans or whatever set spans is to show that the non-homogeneous system is consistent. I'll do example, I'll clarify that. But the non-homogeneous system to the set of equations, because see right in here we have a system, this forms a system of equations, right? Which is of course homogeneous system. So if I can show that the non-homogeneous system, that means if the right side is A, B, C, other than 0, 0. If I show that system is consistent, then that shows that that the set S spans V. All right. Now, for the second part, for linear dependence or independence, we need to show that the homogeneous system has only trivial solution. Okay, so in this case, notice he skips the steps. He says, well, this has only trivial solution. And remember, trivial solution means the system is independent. Therefore, those vectors are independent, satisfy number 2. And of course, they span the set, satisfy number 1. So with these, you can form a coordinate system. So any vector, like vector 4, 5, 6, one vector, coordinates 4, 5, 6, could be actually plotted in this three-dimensional system. X is 4, so you go over 4, to the right 5, and up 6. So there you go. So together, these actually determine a coordinate system. These bases determine a coordinate system. And some of you may remember these as the I, J, K vectors, remember, when we, in your previous courses, like in your third semester calculus or even in pre-calculus courses. Now, the basis that you're looking at is special. Indeed, this is a very special basis. This is called the standard basis for R cubed. In other words, this is a standard coordinate system in the three-dimensional coordinate system. And that's what this does. And the extension of this to the nth dimension also works. So these vectors, if you continue the patterns you see here, you see the standard basis for Rn. Okay, so let me actually do an example right off the bat with you, for you, and so we can clarify this. Now, in my example, so we're in section 4.5, and in my example, this is the example I want to do. I want to show that the vector, so I'm going to make up 3 vectors here, okay? These 3 vectors. Vector 1 is 1, 2, 1. Vector 2 is going to be 2, 9, 0. And vector 3 is going to be 3, 3, 4. So I made up 3 vectors. We want to show that these vectors form a basis for R cubed. Now notice, by the way, the example in the book that he had, the 1, 0, 0, 0, 1, 0, and 0, 0, 1 vectors, that made a basis for R cubed. Here's another basis. So this suffices to say that these bases, by the way, a vector space may have several bases, so the basis is not unique, is the point here. Okay, so what do I need to do? Well, I need to show 2 things. Remember, number 1, we need to show that S spans V, right? Well, for S to span V, I can do it this way. I can show, for this one, we need to show the non-homogeneous system. And I'll show you what the non-homogeneous will look like, is consistent. And how you show consistency of that, I'll tell you about that one. Consistent meaning it has a solution, right? Has a solution there. Because remember, consistent systems have at least one solution, 1 to infinite. Now, to show that it has a solution, usually, typically for this, we're going to show the determinant of A, which is A's matrix of coefficients. In a moment, I'll show you what that looks like. The determinant of A is not zero. So there you go. Now, what does the non-homogeneous system here looks like? Well, the non-homogeneous system is going to be made up of C1V1 plus C2V2 plus C3V3 equals to not zero, but a vector B. Okay, this is non-homogeneous. B is a non-zero vector. So what does vector B, for example, look like in the case of my example in context of what I've made, because I'm in R3. So B, its elements look like this, B1, B2, B3. So we got non-zero, non-zero homogeneous system. Okay, now let's actually write this out. So therefore, remember how this works. You do C1 times V1, C2 times V2, C3 times V3 equal to that. So the system we get is C1 times 1, that's C1, plus 2C2 plus 3C3 equals to B1, right? 1C1, 2C2, 3C3. That's how you get those, equal B1. And so on and so forth. So the next one is going to be what? 2C1 plus 9C2 plus 3C3, and that should equal to B2. 2C1, 9C2, 3C3. Next one, C1, 0C2 is just 0. You don't write that. And 4C3. So the last equation is C1 plus 4C3. That's equal to B3. And this is what the non-homogeneous system is. Now, what am I referencing A here? A would be this matrix of coefficients I was mentioning earlier. So A is going to be 1, 2, 1. The second column is 2, 9, 0. The last column is 3, 3, 4. There you go. Now, the determinant of this matrix, ends up being negative 1. Negative 1, which is not 0. Okay, so because the determinant is negative 1 and non-zero, therefore, we can say that AX equals B, that system, the non-homogeneous system, has a unique solution. And there you go. Therefore, non-homogeneous system has a unique solution, and that is how we show that it spans. That's one way to show that it spans V. Okay. Now, keep in mind, this is the solution to non-homogeneous system. So for spanning, that's what we need to show. Okay. Now, the other condition, number 2, remember number 2 said that the vectors are linearly independent. We need to show V1, V2, and V3 within the set itself. Are there any dependencies between these three vectors? So we need to show that these are linearly independent. And if they are, then we have a basis. So how do I show linear independence? We kind of did that again in the previous section 4.4. For that, we actually look at the homogeneous system. So here, for this one, you analyze the homogeneous system. Okay, so for spanning, you look at the non-homogeneous. For linear independence, you look at the homogeneous system. So homogeneous system is pretty much exactly the same thing, right? Except you have 0, 0, 0. So I'm just going to write C1, V1 plus C2, V2 plus C3, V3 equals 2. There you go, the homogeneous system, where the 0, in my example, in R3, you have 3 components. Each component of that 0 vector is 0 itself. Now, this one, to show independence, for this one, show the homogeneous system has only trivial solution. So trivial solution for homogeneous system, non-trivial for this one, unique solution for non-homogeneous. Therefore, this forms a basis. So it only trivial solutions. Okay, then this would imply that vectors v1, v2, v3 are independent. Okay, and so for the homogeneous system now, actually, I did. For this one, do Gauss-Jordan. Gauss-Jordan on the same A. Remember the difference between homogeneous, this one, and non-homogeneous, this one. This is the non-homogeneous one. Between this system and between the homogeneous system is what's on the right side, correct? Zero versus non-zero. So your matrix of coefficient doesn't change. Therefore, Gauss-Jordan on matrix A actually gave me this, 1, 0, 0, 0, 1, 0, 0, 0, 1. If you augment it with 0, 0 for homogeneous system, you can see that this has only trivial solution. So this would imply that, again, the coefficients C1 equals C2 equals C3 equals 0. This has trivial solution only. Therefore, it is independent. That is the vectors within this. We're talking about v1, v2, v3. We're talking about these three vectors. These are independent. Okay, so here's one example. Okay, now let's take a look at another example just to clarify this work. So for this next example, so we are again in section 4.5. So for this next example now, I'm going to actually look at the standard basis. Let's take a look at standard basis for all matrices that are m by n. Okay, for all mn matrices are m by n. Okay, now my set, I'm going to set B made up of these four matrices, M1, M2, M3, M4. So I have three matrices. This vector has three matrices. What do the M's look like? Let's say M1, I want it to be 1, 0, 0, 0. M2, and I'm looking at 2 by 2s here. Okay, m by n's, this would be 2 by 2 is a subset of that, right? 0, 1, 0, 0. And M3 is going to be 1, I'm sorry, 0, 0 for M3. It's going to be in this second row, first column. M4, let's let it be 0 anywhere except second row, second column. So M3 was second row, first column. And there you go. So we got just basically those elements for each of those matrices. Okay, so this is what we call a standard basis for 2 by 2s. Now, so what do I need to show? Well, I need to show that these m's, 1, 2, 3, 4, are linearly independent. So let's go to linear independence. And then you can show the span. So for linear independence, remember, this is the solution to the homogeneous system, right? C1, M1, C2, M2, C3, M3, and C4, M4. Okay, and then what? And then this should equal 2. What should it equal to? It should equal 2 exactly, the 0, because we're talking about for linear independence. Remember, you look at the homogeneous portion of the system. So it's got to be 0, 0 in the matrix form here. That's what it is. Now, this, we're hoping that this has only trivial solution, right? This must have only trivial solution for it to be independent. If not, then it's not independent. Simple. We can stop and say, no, this isn't a basis. So how do we solve for this one? Well, that's C1 times 1, 0, 0, 0 plus C2 times all of those m's that I made up here. Plus C3 is going to be 0, 0, 1, 0, and plus C4 is going to be 0, 0, 0, 1, and equal to, again, your 0, 0, 0, 0 matrix. Now, again, you're adding four matrices, C1, C2, C3, C4. The way you add matrices, you add corresponding positions, right, elements in the matrix. So it's going to be C1, C2, C3, C4. That's the sum of these four. Again, this is C1, this is C2, C3, C4. When you add, you get C1, 0, 0, 0. That's C1. And here, you get 0, 0, 0. C4 times 1 is C4. Okay, and on the other side, we have just the 2 by 2 0 matrix, right? So from this, again, two matrices are equal. If then the components in that same position must be equal. Therefore, C1, C2, C3, and C4, each of those have to be 0, right? And there you go. And we just show that this has trivial solution. Therefore, yes, it is independent. So it is independent. Now, for the spanning part, M22 span. Let's check this one out. For this one, we need to show the non-homogeneous system has a unique solution. So for linear independence, again, homogeneous. For spanning sets, it has to be the non-homogeneous has to have a unique solution. And for this work, again, we've done the work up here. The result was this matrix 2 by 2, C1, C3, C2, and C4, and we're going to set that equal to non-homogeneous. So we're going to have now non-zero elements, right? B1, B2, B3, B4. And again, from this, we actually get non-zero numbers. So C1 has to be B1, C2 has to be B2, and C3 has to be B3, and C4 has to be B4. And there you go. That is a non-trivial solution. Therefore, yes, that's the conclusion. Thus, M1, M2, M3, and M4, those four form a basis for all 2 by 2 M22, or all 2 by 2 matrices. In other words, every matrix that you make up, 2 by 2 matrix, will be some linear combination of these. See that? This side, the non-homogeneous, is the one you and I make. So I want this to be 2, 10, -4, 0. There you go. You let it be like that. It is possible to accomplish that. Okay, so pretty cool, huh? All right, so we got that one figured out, I hope. And let me see what else. How about, let's do another example. For this next example, let's take a look at, in this example, how about the standard basis? Standard basis for R cubed. Now, the previous one also, remember I had the word standard, which suggests, is there a non-standard basis? The answer is yes. Because again, bases are not unique. These are standard. It's like that's what everybody uses. Kind of think of it as that. Everybody uses these bases. So this is the standard basis for R3 that everybody uses for R3. Think of it as that. To create a coordinate system. Now for this one, my standard basis, I'm going to let it be I, J, K vectors. And what is vector I? That one's going to be 1, 0, 0. Vector J, 0, 1, 0. And vector K, I'm going to let it be 0, 0, 1. Okay. Now, let's talk about linear independence. Right? To show linear independence, again, I still have it up here. We need to show that the homogeneous system has only trivial solution for linear independence. Okay, so let's write the homogeneous system. That means C1i plus C2j plus C3k should equal to the zero vector. So C1i, that's C1 times 1. C2j, C3k. When you combine these, the vector is going to be C1, C2, C3. That's the sum of these, constant multiple of these. And on the right side, we have a three-dimensional vector of zeros, right, in R3. So for this one, again, you can see that this has only trivial solution. C1 equals C2 equals C3 equals 0. There you go. Has only trivial solutions. Therefore, V1, I'm using IJK now. I, K, and J they are independent. Okay, so that's what that would imply. All right, and then let me tidy this up and write this a little better. They are independent. Perfect. Now, that was independence. How about spanning? The set spans R3. So how do we show that? Well, for that, we need to show the solution to a non-homogeneous system, right? Has a unique solution. So that means I'm going to write C1, C2, C3, right? This, for non-homogeneous system, the right side is going to be what? I'll call it V1, V2, V3. Can call it B, whatever, it doesn't matter. So now, if you solve this, what do we get? We get C1 is equal to V1, C2, V2. And remember, these are scalars. These are components of this, there you go, of a vector. And C3 is the third component. And if you think in terms of a homogeneous, in terms of coefficients, the matrix of coefficients looks like this. C1 equals V1, C2 is V2, C3 is V3, right? That's going to be the non-homogeneous system. And for this one, matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. The determinant of this matrix, determinant of A is 1. You simply multiply the diagonals, which is not 0. Therefore, the system AX equals B has unique solution. Again, the two-step process, linear independence and spanning. For linear independence, you're hoping that the homogeneous system has a trivial solution and the non-homogeneous system has a unique solution. And so these form bases. Okay. Now, let me go back to the page of the book and let's focus on our next idea here. Hopefully these examples clarified what we're trying to do here. So now let's look at theorem 4.9. Theorem 49, and the proof of these again is in the book. In the interest of time, so the video doesn't take to be too long, I'm just going to talk about the theorem, but again, clearly the proofs are there. So theorem 4.9 talks about the uniqueness of a basis. So suppose you have a set of vectors in S, and now S here is a basis. Remember, a basis is just a set that has a bunch of vectors in it. A basis for the vector space, if this is a basis, then every vector in V can be written in one and only one way as a linear combination of these. So think about your standard basis ijk that we just looked at. Every vector in 3 dimension can be written as the linear combination of the ijk's that I had in my previous example. So that's what this one says. So that's why we like bases. Now, then there's our next theorem, theorem 10. This one, basis and linear dependence now. So suppose we have a basis. That means every vector again in vector space V could be written as a linear combination of these. So let S be a basis for that vector space. Then every set containing more than n vectors is in V is linearly dependent. So in other words, it suffices to have only n vectors in the basis. If you have more than that, then the set is going to be linearly dependent. And we ran into this before, the situation. Remember, previous lectures that I did examples with, we ended up sometimes having a system that, let's say we have 3 unknowns but 4 equations, or 2 unknowns and 3 equations. So this theorem exactly addresses that. If I have a basis, let's say for 2 equations, 2 unknowns, that's all you need, 2 equations. So with 3 equations, each equation represents a vector. So if I have, for a 2 by 2 unknowns, I have 3 equations, 3 vectors. So if I have more than that, more than 2 in this case, then that means those vectors are linearly dependent in that system. Okay, so that's what that means. Theorem number 11. Number 11. Number of vectors in a basis. How many vectors are in a basis? Well, if a vector space V has one basis with n vectors, then every basis for V has n vectors. Okay, so let's say, begin for ijk, we had 3 vectors. Then every basis in V has 3 vectors because that was a basis. So in other words, all the bases have the same number of vectors. Okay, all bases. And remember, basis is not unique. So if a vector space has a basis with n vectors, see that just one basis, and every basis will have n vectors, which again suggests, can there be more than one basis for the same vector space? And the answer is yes, it could be more than one. Okay. Now we talk about often the standard ones. The standard ones are the ones that all the work is pretty much standardized upon, normalized upon, and accepted by the masses. Okay, now let's talk about the dimension of a vector space. So what is the dimension? The dimension of a vector space is simply the number of vectors that are in the basis. Okay, so here if you have a vector space V, suppose it has a basis consisting of n vectors. Again, a good one to kind of recall is the ijk in R3, right? ijk are 3 vectors, and ijk form a basis. So it's 3 vectors. That's your n. Then we say that the dimension of the vector space, that's the dimension of R3, is n, is 3, because there are 3 vectors in the basis. Okay, so there you go. The dimension of the vector space is the same as the number of vectors in the basis. Now, look at the examples. Look at the dimension of our n, where the standard operation is n. Now, standard operation here, notice it says the standard. What are standard operations? When we talk about standard operations in this context, standard operations for us are addition and scalar multiplication. Two operations, addition, scalar multiplication. Now, look at number 2, the dimension of Pn. Remember, these are polynomial, nth degree polynomial. So for example, if you have a quadratic equation, forget the equation, a quadratic polynomial, a second degree, n is 2, then standard operation is n plus 1. Then you say, well, you said n second degree polynomial. Why is it n plus 1? That means 3. Well, because a second degree polynomial, remember what it looks like? It looks like ax squared plus bx plus c plus plus c, the constant, right? So a second degree polynomial, for example, x squared plus 2x plus 5. That's a second degree polynomial. X squared plus 2x plus 5. Aren't there 3 terms? So the dimension of a second degree polynomial is 3. If you look at the matrices, the dimension of an m by n matrix is m by n. It's the number of elements in the matrix. So that's, in other words, that's how many vectors it takes to explain and account for every vector in the matrices that are made up of m rows and n columns. You need exactly m by n vectors. Okay. So let's see. So there you have that one. What else? I'm trying to think if there's anything else I need to add to this. So again, the takeaway from this so far is that if a basis has more than n vectors, then the set of S is linearly dependent. I talked about that one. Now, if the set of a basis, by the way, has fewer than n vectors, then it doesn't span V. So here's the case. For instance, let's say I have 4 unknowns and only 3 equations. 4 unknowns, 3 equations. So that set of those, the set of vectors in that set do not span V because I have fewer vectors in my basis than it is in vector space V. Okay. Now, so here we defined V. Dimension of V is n, again, the number of vectors in the basis, right? For V. Now, by the way, if the vector space has just a 0 in it, the dimension is 0. Remember, dimension is a scalar. Okay, so here, these are scalars. Now, what else? Let's take a look at, I think, and we'll go exercises. Let's look at number 12 now. Number 12 is actually a very interesting, very useful theorem. And this is the last theorem of the section. Theorem 12 says, this is the basis test for n-dimensional space. Now, remember, to be a basis, we said the set must span V and the vectors within S must be linearly independent, right? Which is number 1, and number 2, what you're looking at. Well, this theorem says that the vector space of dimension n, if S is linearly independent, then S is a basis. Boom, just based on that number 1. That's it. You don't need number 2. Okay. Number 2 says if the set S spans V, then it is a basis. Okay. So there you have it. You don't need the test for basis. You only do one or the other, And again, it's up to you. Most common is number one that the author has written. You show the set is linearly independent. So remember, you don't have to do both. You do one or the other. Okay. Now, let's see. So I talked about number 12. Okay, I think we can now go to actually to the exercises here. Let's see, yeah, we go in the exercises. So let's take a look at some of these exercises now. Okay. Okay, so let's begin with how about we're going to do several of these. Okay. So for instance, I'm going to do how about number 2, simple ones. I'll write these down, by the way, and then I'll read the problems. Okay, so remember, in the first 6 exercises, it says write the standard basis. So in other words, what in R2, for instance, or R4 in this case, number 2, standard basis means come up with 4 vectors that every vector in R4 could be written as the linear combination of. Okay, now standards are the ones that everybody uses. Okay, so I'm going to do these problems and they will go rather quickly. So let me switch to my share to my notebook here. All right, or just my notes. Okay, let's do this. So we're looking at section 4.5 exercises. Okay, exercise number 2, for instance, we want a standard basis in R4. Okay, so that means R4 requires 4 vectors, right? Because that's the dimension of that space. So I need 4. If I write 3, that's not enough. So standard ones are these. Think of your I, J, K vectors, okay? 1, 0, 1, 0, 0. And let's say if I stop there, because it's in R4, I don't have enough vectors, so that's not going to make a basis. 0, 0, 1, 0. If I stop there, it's not enough. I need 4 vectors. So I'm just going to keep going. Just one more, and there you go. Now, what if I keep writing? Suppose I write another vector, 4 dimensions. So I'm going to have like 1, 2, 3, 4. That one would be extra. Remember, we don't need 5 for an R4. If you do that, that means there is a linear combination among the set itself, and it violates the definition of a basis based on number of vectors in the basis. Okay, so 4 vectors in R4. What does, for instance, this other one look like? Let's say I'm looking at the book. So it says M41. Number 4 is that one. M41 means the set of all matrices that have 4 rows, 4 columns. So a basis for this would be as the vectors, you can go 1, 0, 0, 0, right? 4 rows, 1 column. Or I can go 0, 1, 0, 0. Or I can go 0, 0, 1, 0. And the last one would be this one there. And that would be the basis. How about, let's say, number 6? Number 6 is P2, the basis for second-degree polynomials, right? Now, for this one, remember, again, a polynomial is like this, ax squared plus bx plus c, right? That's, oh, I'm so sorry. I want to make sure. Yeah, okay. No, I'm good. I thought I was looking at the page of the book with the exercises and didn't see it correctly. I thought I wasn't sharing my notes with you. Okay, so remember the second degree polynomials look like this. So they have 1, 2, 3 elements in it. right? Yeah. So I need three vectors, don't I? 1, 2, 3. One that picks up the constant, one that picks up the x term, the linear term, one that picks up the second degree term. So the standard basis for P2, therefore, is going to be 1x squared. In other words, every second degree polynomial, like if I say it's 3x squared minus 4x plus a half, there you go. It's going to be in here. The constant is a half, right? So it's going to be a half times 1. Coefficient on x is -4, so -4x. Coefficient on x squared, 3x squared. So it's going to be C1, 1, C2x, C3x squared. And there's your basis. Okay, so we got that one. Now, the other ones I'm going to look at. Let me switch to the page of a book so you see what exercise heading is. In this one, number 7 through 14, let's take a look at a couple of these. It says, explain why S is not a basis in R2. Why is it not a basis in R2? So number 12 says, let's say my set S is 4, -3, and 8, -6. Okay, now in R2, remember, R2 means we need two vectors, correct? So for instance, number 7, number 8, right? The basis in R2 can only have two vectors, right? So number 7 and 8 are not. The reason, because you have three vectors. In R2, you can only have two vectors, not three. Now, number 12 is the one we want to show, and then number 14, let me write that one, and we'll see what makes these not correct. Well, you can see number 14 already. I don't need to, I wrote it, but I mean 13 and 14. Remember, in R2, you need exactly two vectors. 7 didn't work, 8 didn't work, add too many. 13 and 14 won't work because, well, let's see, you can't have too many. Actually, and for this one, let's actually show why number 14 doesn't work. Let me explain that one. So let me switch my share, and there you go. So let's actually do number 12. For number 12, and remember theorem 12 that we looked at. It just happens number 12. Number 12 matches our theorem. Theorem 12 said in order to show that S is a basis, either show that it spans V or the set is linearly independent. So for this one, let's show linear independence. This is V1, this is V2, my second vector. If you look at the second one, don't you multiply 4 times 2 to get 8, -3 by the same number, 2 get -6. So here I can say vector 2 is twice vector 1. Therefore, it's linearly dependent. So it cannot be a basis. So it doesn't span. If it's linearly dependent, it does not span. Span R2, therefore not a basis. See how that works? Now, number 14, let's see if this is, how about this one? Is this vector linearly independent? Right? So for this one, it is actually the vector is linearly independent because there's only one vector, but it doesn't span R2. Here's why. This one does not span R2. Remember, to span R2 means you can write every vector as a linear combination of these two, right? So for instance, for this one, if you look at vector 1, 1, it doesn't belong to the span of S. Okay, because here's why. It's impossible because it has to match, right? This is not in the form because this is in the form -1, 2, and a constant multiple of that. So here's what I mean. C1 times -1 plus C2 times 2. That should equal to 1, 1. True? So let's see how this is going to work. Let's see. Okay, so yeah, here's the thing. This set is actually linearly independent. Okay, 1, 1 is not in the span of S, and I'll explain why. So it doesn't span R2, but it is linearly independent, right? Because I can write this vector as, let's see, negative C1 must be 1. So C1 is -1, and 2C1 should be 1. So C2 is a half. So that's fine, actually. So it is linearly independent, but remember, it also has to span. It doesn't span means cover every vector in it. And here's why. To span R2, a set of vectors, right, must be able to generate any vector in R2 using linear combinations. Well, this requires that we have at least two vectors. So we need at least two vectors. Okay, we need at least two vectors. Well, -1, 2 is a single vector, right? So this can only form scalar multiple of itself, right? Just like we showed here, scalar multiple of that, of itself. That's all it can do. So it only spans a one-dimensional subspace, in other words. And what does that one-dimensional space look like? That would be just like a line through the origin, right, through 0, 0 in direction of -1, 2. So it doesn't span two-dimensional space. Okay, so again, to span two-dimensional space, I need two vectors. I cannot have one. All right, so there you go. That's number 14. Now let's take a look at this one. Okay. And let's see. Let's try within number 14. Let's take a look at the next segment in here. How about, I don't know, number 20, for example. It says explain why S is not a basis for R cubes. Remember R3, so we need exactly 3 to span it. Exactly 3 vectors. So 15 is a potential, 16 is a potential, 17 is not. See, it doesn't span. You only have 2 vectors, right? We need 3 vectors. 18, 2 vectors, doesn't cover it. 20, number 20, I have 1, 2, 3, 4. 4 vectors. I've got 1 too many, which makes within these vectors themselves are linearly a linear combination of themselves. All right, so let's see, for instance, the one that has a potential of being, let's do number 16 actually. So I'm going to write number 16 down first, and we'll work it together. In number 16, I have 2, 1, -2, and then -2, -1, 2, and then 4, 2, 4. 4, 2, -4, that is. Okay. Let me go to my note. So here's my notes now. For number 16, so what I'm going to do in order to show that it is a basis, if it is a basis for this, remember, all we need to do is show linear independence by that theorem. We don't need to show span or the other, as long as it's one or the other. So let's see if these are linearly independent sets, okay, for the basis. So here's my set. I'm going to set up the coefficients. The coefficient would be what? 2C1 minus 2C2 plus 4C3 equals 0. For linear independence, remember, we look at the homogeneous system. For spanning sets, we look at the non-homogeneous system. So let's take a look at the homogeneous first of all. Plus 2C2, negative 4C3, and that should be 0, right? Again, 2C1, negative 2C2, 4C3 should be 0. And then multiple of this one should be 0. This one should be 0. The homogeneous system. Now, this one, if you go to, let's say, Gauss-Jordan. If you do Gauss-Jordan on this one, this is what I got. I got 1, 0, 0, negative 1, 0, 0, 2, 0, 0. Okay, so I have a row of zeros here. So actually I have two rows of 0, this one and this one. And remember, this is a homogeneous system, so you got 0, 0 there. That means coefficient on C1, coefficient C2, coefficient on C3. So this means I'm going to have to let C2 and C3 be my free parameters, right? Therefore, I'm going to let C3 be T, C2 be S. Those are the free parameters. And C1 is going to be move C2 to the other side, C2 plus minus 2C3, right? Once I move them to the other side. And C2 was S, C3 was T, negative 2T, and here we have the solution. So I can therefore write these vectors as a linear combination of these other ones. Notice this one has non-trivial solution, right? This is a homogeneous system, and the solution is what? The solution set, because I have S and T, so I'm going to have two vectors, S, S, 0. Let me write this. C1 is S minus 2T, C2 is S, C3 is T, right? So to write this one, I'm going to go S plus negative 2T. So S plus negative 2T picks this one up. This second one is S, so the coefficient on T would be 0 here, and this is T, this is S must be 0, so that's just T, right? Which really I can write it as SS0 plus factor the T out, negative 2, 0, 1, and there you have it. This will give you, what do you call it? This is how this set could be written as a linear combination of the other vectors. Therefore, long story short, S is linearly dependent. Dependent on this one, right? Because the solution is not trivial. So this is going to be linearly dependent. And you can see there are many, many solutions to this one. It doesn't have trivial solution only. S is linearly dependent. Again, that means non-trivial solutions. That's what that means. Okay, therefore, it's because it's not linearly independent, the set is not. Therefore, this one does not form a basis. A basis for R3. Okay, and there you have that one. Now, let me see if I can, let's go to the book and see if we can find another one to work. So that's how you work this segment. And these other ones, again, there's so many exercises here, folks. Let's take a look at, I don't know, number maybe 24. Let me write down number 24, section 4.5. Number 24. In exercise number 24, the set is 6x minus 3, comma, 3x squared plus 1. Oh, I'm sorry, 3x squared, comma 1. 3x squared, comma 1, comma Well, that is 1 minus of the quadratic. It's 1 minus 2x minus x squared. So there's the set, right? So I got my first, second, and the last components. Now, ys is not a basis for P2. Okay, so let's see. Let me go to my notebook. So here's the set. Now, why is it not? Well, let's look at the linear combination of C1V1, C2V2, C3V3 equal to 0 in this case, right? 0. Now, that means I have C1 times 6x minus 3 plus C2 times 3x squared plus C3 times the quadratic, 1 minus 2x minus x squared. Okay, we're going to set that equal to the scalar 0 now. And the coefficient on this, again, matching constant term, coefficient on x term, and coefficient on x squared. So I'm going to get 3c2 minus c3 equals 0. And then I get 6c1 minus 2c3 equals 0, and negative 3. Let me space it equally. So negative 3c1 minus c3 equals 0. So for instance, where does this come from? Look at the coefficient on x squared, 3c2. 3c2, and then here the coefficient on x squared is negative c3, right? So it's negative c3 and 3c2 actually. So that should be different, right? Let me make sure I got this right. The constant, negative 3c1 plus c3 is 0, correct? Okay, hold on. Let me pause this and fix this thing up here for you. Just a moment. Okay, guys, I figured it out. I just didn't carry the the signs correctly. So this is actually now the correct sign that I have. So again, the constant, negative 3c1 and c3. That's going to be plus here. The x term 6c1 and the x term negative 2c3. That's this one. And the x squared term is 3c2 minus c3. So that looks great. Now, the Gauss-Jordan form of the homogeneous system is going to be 0, 1, 0. I got negative a third, and negative a third is 0. And again, we have a row of zeros, which again, that's the sign that one of these vectors is a linear combination of the others. So I'm going to let the free variable C3 be t. And remember, this is coefficient on C1, C2, and C3. That's what those coefficients are. So C3 is t. C2 is going to be 1/3 t and is equal to C1. Again, remember, this is homogeneous. So the second equation reads 1c2 negative 1/3 c3 is 0. So when you move it to the other side, it becomes 1/3 c3, and I'm letting c3 to be t. Same thing for this one. C1, move this to the other side, becomes 1/3 t. So I can actually write a solution now for this one, right? And what does the solution look like? The solution set is going to look like the following. It's going to be t factored out. C1, C2 are the same, 1/3, 1/3, and C3 is 1. And there you go. So the system has infinitely many solutions, right? In this one, it has infinitely many solutions. So there is non-trivial solution to this one. It has non-trivial solution, and this means that the system is linearly dependent, therefore not a basis. They have to be independent. So that's not a basis. Now, let's see. Let's take a look at another one. So I'm going to change my share to, again, the page of the book. Boy, let's see. Again, there are so many of these. How about, okay, now, for example, numbers here, the geometrical one, determine whether the set is a basis. Remember, if the vectors are collinear, it's not a basis. These are two are collinear, they're not. And they must actually be on the, there have to be non-collinear for R2, that's simple. So 29 is indeed a basis, right? And 32, they're linearly independent is a basis. These two, 30, 31 are not because they're collinear. Same direction, and number 30 go opposite direction. That was easy. Okay, now let's take a look at something from this segment. Let's take a look at number 36. In number 36, determine whether S is a basis. So for these, we can pretty much look at some of them and answer. In number 36, for R3, remember basis, we need to have three vectors. Not enough, only two. So 36 is not a basis. These vectors would be linearly independent. Okay. Now, for number 38, for example, this one, we could work that one out. Let's take a look at number 38. In number 38, the set S has 0, 0, 0, and then it has 1, 5, 6, and 6, 2, 1. So it does have the number of vectors that's required. So let's check this one out and see if this will work. Number 38. So I'm going to go linear combination of these. C1, V1. And remember, the reason we're not checking for a span is because the theorem we had. We only need to check one or the other for the basis. Okay. Now, the span of this set is 3, right? Span is 3, the number of vectors. So let's check it out. So how is this going to look like? The matrix is going to be C1 times 0 plus C2 times 1 plus 6C3 equals 0. Okay, so that's how you write the system. So I'm going to have 0, 1, 6. The second row is going to be 0, 5, 2, and 0, 6, 1, right? So my matrix is therefore 0, 0, 0, 1, 5, 6, and 6, 2, 1. Now, if you do Gauss-Jordan, notice, by the way, you have a column of zeros. So that means the determinant is 0, right? Based on that, if you expand about the first column, I'm going to say, note, determinant of A is 0. Determinant of A is 0 in this one. So that means you have non-trivial solutions for this one. Okay, determinant is 0. But let's actually do Gauss-Jordan. The Gauss-Jordan for this is going to actually give us 0, 0, 0, 1, 0, 0, and 0, 1, 0. Okay, that is the Gauss-Jordan form of this. So from this matrix, from the Gauss-Jordan, we see that C1 clearly could be anything. Remember, on the other side of this is 0, 0, 0. So C2 and C3 are 0. C1 could be anything, right? C1 is T, because 0 times anything is 0. So for this one, we have non-trivial solution because C1 is T. In other words, the matrix, the vector T 0, 0 works. And there you go. So we have non-trivial solution. If there's non-trivial solution, then that means the set is dependent. And you always see that from the Gauss-Jordan form. See, a row of 0 means a set is dependent. Therefore, it has to be linearly independent, right? To span. So this does not span R3. Okay. Now, let me go to the book again and see if we find anything that's materially different. So for all of these, pretty much you just do the linear combinations, right? Let me see here. Let me go back up. How about, I don't know, number 48, actually. Let's try number 48. Hopefully that's different than the others. So I'm going to write this one in my note. We're doing section 4.5. And we're looking at number 48. Okay, in exercise 48, we have a set of vectors, 48. It's 1, 0, 0. The second one is 1, 1, 0. And the last vector in the set, 1, 1, 1. The question, determine whether S is a basis for R3. If it is, then write U. Good, this is different. Let me say if a basis, then write vector U given by 8, 3, 8 as a linear combination of the vectors in S. Remember, that's the whole purpose of a basis. So we can write every vector in the vector space as a linear combination of the vectors in our basis. So let's check this one out. And this will be the last exercise, by the way, folks. We'll be done after this one. And I'm not sure why this is kind of dark here. I realize, but I'm not sure what to do here, folks. Let me see. There you go. I don't know what I did, but sorry about the image being so dark. But anyway, better late than ever, huh? So this is in section 4.5. Now, let's take a look at number 48. In number 48, I have the sets. So what do I need to do? Let's do the linear combination of these. C1, V1, C2, V2 plus C3, V3. And we're going to set that equal to 0. That's all we've been doing mostly in this section, right? Now, here's C1, C2, C3. C1, C2, C3, C1, C2, C3. Each of those scalar multiples of C1, C2, C3 should equal to first 0. We're not doing this yet. We're not doing this part yet. Okay, so what does my matrix going to look like? My matrix in number 48. So it's going to be, let's see, C1. First, let me write this. C1 plus C2 plus C3, right? The first component, C1, C2, C3 must be 0. And then C1, 0, that's 0. C2 and plus C3 is equal 0. And finally, 0, 0, 1, C3 is 0. So here's my system. As you can see for this one, the matrix form is 1, 0, 0, 1, 1, 0, and 1, 1, 1. Right, that's what the matrix form looks like for the homogeneous system. So from this, C3 is 0. From the second equation, C2 is negative C3. And from the first one, C1 is negative C2, negative C3, right? And these must be 0. 0 because C3 is 0. C3 0 makes C2 0. C2, C3 are both 0, so C1 would be 0. Therefore, solution is C1 equals C2 equals C3 equals 0. Okay, we got that one. Now, because this has only trivial solution, right? If they're all 0, they're trivial solutions. Therefore, the set, therefore, S is linearly independent, right? The set is linearly independent. That means S is a basis for R3. And there you go. So the I, J, K aren't the only ones that work. This one works also. Every vector in R3 could be written as some linear combination of these three. And it tells you, well, that's what this means. Okay. Because they're linearly independent again. Now, let's do the second part. This was the first part. The question said, if it is a basis, then let's do it. You just said every vector can be written as a linear combination of these three. Let's see if it works for this one. So what are we going to do for that one? We're going to actually write the system. Remember, we have 1, 0, 0, 1, 1, 0, 1, 1, 1. And this is now a non-homogeneous system. You set it equal to 8, 3, 8, and try to solve this, right? Now, when we solve this one, you go through and do Gauss-Jordan. Again, this is the non-homogeneous system. Non-homogeneous system. When you do Gauss-Jordan on this one, what are we going to get? The Gauss-Jordan of this. Oh, well, let me actually rerun this one. I want to make sure my numbers make sense. Just a moment here, folks. Hold on. Okay, folks, I'm back. So here it is. This is the Gauss-Jordan. I just want to make sure I had the right numbers. You can see, by the way, from the third equation that C3 is 8. You can back substitute. I just want to use the software, and I did, and this is what I got. So, so what do we do next? This one, therefore, has a solution, doesn't it? The solution is C3. Let's write the solution. C3 is 8. What is C2? C2 is equal to -5, and C1 is equal to 5 from the Gauss-Jordan. Okay. Now, this is what we're claiming, that vector U, which is 8, 3, 8, could be written as the following linear combination. C1 times vector 1 times 1, 0, 0, plus C2, -5. -5 times the second vector is 1, 1, 0, right? This one. And plus C3. C3 is 8. 8 times V3, the third vector in the set. And there you have it. That's the linear combination, and we can verify it works. Just real quick, and this is all the question asks for. Write it as linear combination. This is the linear combination. And to verify, you get 5, 0, 0, plus -5, -5, 0, plus I'm distributing. 8 times 1, 1, 1 is 8, 8, 8. And when we add vectors, we add like components, right? So go 5 minus 5, 0 plus 8. That's 8. 0 plus -5 plus 8. That's 3. And 0, 0, 8 is 8. And indeed, we just showed that's what U is. So this is the linear combination. So U, in this case, in 8, 3, 8 is 5 times vector 1, negative 5 times vector 2 plus 8 times vector 3. And there you go. That's all we have to do. So again, there's so many of these exercises, so please do try them. Again, in the interest of time, I can't do too many. The video is already too long. So thank you for your attention, everyone, and please try some of these exercises, and we'll talk later. Goodbye.